Hi, Integrated Math 1. Welcome to lesson 5.2.3b. We're doing day 2 of our reflections as functions. Yay. So we are going to keep this going. We've already discovered that our line of reflection was the perpendicular bisector of our segment when we went from one point to our reflected point. So we're going to take that to the next level today. You are going to want straight edge, compass, all that good stuff. You are going to want your workbook and a pencil, of course. If you don't have those things, go grab them real quick and then we'll keep going. So it is possible to construct the line of reflection when given two figures that are reflections of one another. So up to this point, last time we were given the line of reflection, we're given one of the figures and then we were reflecting it. But what if I give you the two figures and I'm like, where's the line of reflection? It's possible to do that as well because we know it should just go right down the middle perpendicular to the two figures. So page 83 and actually going over onto page 84, I've got a couple of these for you on number 6. I want you to determine whether the figures are reflections of one another. And if they are reflections, identify that line of reflection. Go ahead, hit pause, work these out. There's a couple of them there on number 6, and then hit play when you're ready to check your work. Now, this isn't going to be very good because I'm using my tablet, but you get the idea. I can see that if I folded it right down here, it's not very good, but if I folded it, this is not my best line ever, right along this line, I should get reflections of these two. So I would say, yeah, these figures are reflections of one another. I could draw a line right down the middle and be like, boop, fold it. It's a reflection. For B, I tried that. I tried drawing a line down the middle. Oops. Oh my gosh, my lines are getting worse. Sorry. Erase all that. But what I quickly realized is folding it wasn't going to work. That the one is upside down from the other, that if I fold it, they're not going to be right on top of each other. So those pentagons are not reflections of one another. Part C, I tried that again. I was like, well, I have this guy and this guy. But I also realized that if I draw a line in between them and I were to try to fold it along that line, they wouldn't be reflections, right? That tip would hit that side and that vertex would hit that side. They wouldn't fold nicely on top of each other. So these triangles are also not reflections of one another. Fair enough. That happens sometimes. So now that we've got these reflections back in our head, that I know I should be able to fold it and they should map right on top of each other. Let's keep going. Page 85. So in the getting started activity, we saw that the perpendicular bisector of a line segment is the line of reflection between the endpoints of the line segment. All right, so we're going to kind of come back to this picture here on page 85. We know that the perpendicular bisector is our line of reflection. We know that's how it happens. If I were to fold along line T, R and B would be like right on top of each other. So here's what I would like you to do. I would like you to label a point anywhere on line L here. Anywhere on line L. I know I called it line T. It's line L. Anywhere on line L, can you put a point P over here, over here, over here? I don't really care, but somewhere, can you put a point P on this line? And then I want you to see if you can find a relationship between P and R and B. Go ahead, hit pause, put down your point, jot down some thoughts, and then hit play when you're ready to check your work. Now, your point P might be in a different spot than mine. I went ahead and I put it right here, and I'm like, cool, there's point P, yay. And I was looking at this and realizing that the distance from P to R looks like it's pretty close to this as the same distance from P to B. This is not my best drawing ever. I apologize. But it looks like it's about the same distance. At point P appears to be the same distance from points R and B. It's very interesting. What you've actually found is something called the perpendicular bisector theorem. You can prove that the endpoints of any line segment are equidistant from any point on the perpendicular bisector. So P could have been here or here or here or here or here. It doesn't matter. The distance from P to R should be equal to the distance from P to B. This right here is what we call a proof. We're gonna do a lot of this in this class. You're really gonna dig in next year when you're taking integrated math 2. A proof is a series of statements and corresponding reasons forming a valid argument, okay, that starts with a hypothesis. This is my hypothesis. Hey, anything, L is a perpendicular bisector, P is a point on that line, and arrives at a conclusion. Our conclusion is that PR should be equal to PB. So we have a whole little proof here. Given that I've got a perpendicular bisector, given a point on that perpendicular bisector, I know PR should be equal to PB. And so this is what we call a proof, where we go through and say, hey, the reflection of point P across the line is point P, right? If I were to fold on that line, P is not going anywhere. Because line L is the perpendicular bisector of RB, the reflection of R, it goes on to B, and so PR should equal PB. This is the perpendicular bisector theorem. It states that any point on the perpendicular bisector of a segment is equidistant from the endpoints of that segment. A theorem is what we just did. A theorem is a statement that can be demonstrated to be true by accepted mathematical operations and arguments. So a theorem is like, oh, I can prove this is true with math statements that we already know. So let's consider the relationship between endpoints of a line segment and any point on the perpendicular bisector, just kind of from another perspective. So suppose you have 2 points that are equidistant from a third point. You can show that the third point lies on the perpendicular bisector connecting the segments. I'll show you what I mean. If you come over here to page 86, here I have point Q, and it's equidistant from A and from B. Okay, the distance from A to B, from Q to A is the same as the distance from Q to B. So here's what I want you to do. I want you to bisect this angle. Okay, that's step 1. Bisect the angle such that you're going to make 2 congruent angles. And then I want you to label the intersection of QP and AB as point C. I'll show you what start by making the bisector, and then I'll show you the rest of what it means. Go ahead and hit pause, bisect this angle, hit play when you're ready to check your work. All right, I'm going to switch to my camera so you can see what I'm doing. Ooh. Give it a moment. Good job, little camera. So I'm going to start just by bisecting this. If you recall, we wanted to make sure we did a swipe that hits both sides. You guys did such a good job with this in the last unit. So I'm going to make an arc that touches both sides. That's step 1, right? And then I'm going to use those points. I'm going to use this point and this point, the points on each side. I usually like to extend it out, make it a little bigger. And I'm going to go ahead and put the stabby guy on one side. That's too big. Making a mark out in the middle somewhere. Oopsie, I slid. And then I'm going to go to the other side, make a matching arc from the other side. There we go. There we are. I'm going to call this point P. Said to draw QP, so I'm going to call that point. Said to call that QP, so I'm going to call that P. I'm going to use my straight edge. And just be like, whoa, maybe I'll be like something. Woo, there it goes. And you bisected the angle. Now, the next directions were confusing. That's okay. That's why I'm here. So this makes angle BQP and angle PQA. These guys are congruent angles. We know that. We're good and all that. So what I want to do now is label the intersection of QP and AB. I'm going to connect A to B, use my straight edge. We're going to call that point C. Okay. So now you've got something like this on your paper. I've got triangles and all kinds of cool stuff. And we just bisected the angle. And then I connected the sides, and I'm calling that point C. So it looks like this. Yay. This is interesting because these two sides are equal. This should be the perpendicular bisector. Let me grab my little pen here. So because these two sides are equal, because QB is equal to QC, because Q is the same distance it is from B as it is from A, that means that C is the midpoint of A and B. It also means this should be perpendicular. Ah, it goes the other way. How snazzy is that? It's snazzy. So you've learned that reflections and translations are isometries, right? Which means they preserve distance and angle measures, right? When I reflect something, I don't change the angles, I don't change length, I'm just reflecting, I'm just flipping it. When I translate something, I'm just sliding it over. I'm not changing the size or the shape. So they're isometries. They keep their size, they keep their shape. So here's what I would like you to do. It turns out you can do more than one thing. So I would like you to describe and sketch the sequence of translations and reflections that shows that the two figures in each pair are congruent. And the images are shown with dashed lines. So I want you to show me that these two guys are congruent by describing, hey, it was reflected over this kind of a line, and then it was translated up or down or left or right. Go ahead, hit pause. Work these out, just give me your descriptions, and then hit play when you're ready to check your work. All right, so I was looking at this. We have a couple of these. This is, by the way, is what your homework is going to be like. And I realized very quickly that there is a reflection here, right? That it looks like I've got a vertical line of reflection, right? Flip to flip. But I can also see it went up, right? C is down here, but D is up there. So it looks like I went up just a couple of units. So I said that if you reflect ABC across a vertical line and then translate it up, you have congruent triangles. And that's all I want, just a description of what happened. So for part B, I was looking at this and I thought, how would this work? And I thought, if I did a horizontal reflection, so if I flipped it this way, if I was like, this goes here, right? And then they flipped, but then I scooched it over, right? I scooched it over so that they hit on their long sides like that. That would work. So if I reflected triangle ADC across a horizontal line and a vertical line, and then translated it. So I'm going to do a double flip and then scooch it over. That works. Nice. What if I put it on a coordinate plane? Would that make it easier? I find it's easier for me on a coordinate plane. Can you do this again, only now you've got it on a coordinate plane? Describe the sequence of translations and reflections which would map the pre-image, the original's PQR, onto the image triangle ABC. How we get from here to here. And you can be nice and specific this time, right? Because we've got numbers. We've got a coordinate plane to play with. Go ahead, hit pause, and see what you can do with this. Hit play when you're ready to check your work. So I realized that P to the y-axis is the same as the distance from A to the y-axis. So I was like, hey, the y-axis is my line of reflection. So I have a y-axis as a line of reflection, but I also realized that we went down, right? How much? If I'm up here, because if I just reflect, I should be up here, but I ended up going 1, 2, 3, 4 units down. So it looks like I need to reflect over the y-axis and then translate down 4 units. That would give me my new shape. Nice. As always, guys, I hope you found this helpful. Hope you found this useful. If you got questions or concerns, come talk to me. I'll see you guys soon. Bye.